Our topic this evening is technology, specifically the practical and inspiring technologies spinning out of Berkeley Lab that have particular pertinence to people in the developing world. A new institute at the lab, the Institute for Globally Transformative Technologies, I know a mouthful, also called LIGHT, is helping to identify and speed into existence a variety of simple, powerful, practical, and creative inventions aimed squarely at the root causes of global poverty.
On the 8th of February this year, at White House, there was an announcement that this kind of work is now being turned into a systematic, organized way to take our best minds in science and engineering technology to address problems at the bottom of the pyramid, to do the last mile of research that otherwise never gets funded. Because nobody votes for that kind of funding, Berkeley Lab said, we will take this on because it's important for the world, it's the right thing to do to provide a low-carbon, high-efficiency trajectory for the bottom 2 billion people to reach a standard of living that we consider essential for anybody in modern society.
Today, in 2012, there are 870 million people who will be chronically starving. They just will not have enough to eat. Often they live on World Food Program aid. There are 25 million people in this year who live in refugee camps. And this is not poverty. This is significantly worse than poverty. 16 million people by the end of this year will die because of these diseases. Often the medicines are there, and we'll see why it is so difficult for these medicines to reach these individuals. From the moment we get up, we have technology. We have alarm clocks, clean water, automobiles, air conditioners, flushing toilets, refrigerators. And there is so much we take for granted that simply does not exist. It almost, when you go to some of these countries and you visit some of these communities, it really feels like they're living in a different century. What does a breakthrough look like? First of all, it has to work in the absence of electricity, reliable electricity anyway. Number two, it has to be hugely affordable. Number three, it has to be robust. And even if we do all of those things, it's not like there's a Walmart that we can send these things to, right? There is no mechanism for distributing these things. And so that's what we have to do to come up with breakthroughs. And so our model is we identify, we discover, we develop, and we deploy scientific and technological breakthroughs for sustainable global development. First of all, there are a few really interesting technologies that we know are important and interesting. There's huge demand for. And we have a small portfolio of those projects, and we'll see 4 examples of that today. Then we're stepping back and saying, what really matters? What are the most critical scientific and technological breakthroughs that are required for solving these problems?
Global development is extremely complex, and there are many problems within development that technology is simply not applicable to. But there are many, many problems where technology is a key component of the solution. And oftentimes what we see within these problems is that when the right technology is developed, we can have a massive and rapid impact on people's lives. Oftentimes when we find science and technology being applied to global development challenges, the solution was actually developed before the problem was really understood, or in often cases before the people developing that solution even understood that the problem existed. So this is something that we're very cognizant of at LIGHT, and it's a paradigm that we refer to as hammers looking for nails. When you're a hammer, everything looks like a nail. Because from our perspective, this is part of the reason why oftentimes technologies that are high potential never quite live up to their expectations.
So this, my friends, is the world's first portable, solar-powered vaccine refrigerator.
So let's just look through the journey of a small vial of polio costing about 11 cents, and it takes about 11 months of journey to go from the national level storage depot through the state, through the division, through the public health outpost, and then add to it some more months before it reaches the final end of chain. Now, throughout the life cycle of this vial, before it gets inoculated into a baby, it must retain a very narrow temperature range of between 2 to 8 degrees centigrade. And this is called the vaccine cold chain. And because of these kind of transportation and this kind of end-use scenarios, we have to very carefully figure out what it is that will take the vaccine all the way from lab to jab.
So we could make it possible to keep the vaccines cold for weeks at a time between the delivery times. That would be something really new. So we decided that we wanted our vaccine cooler to not just be a transport system, but we wanted it to also be able to store the vaccines at the end of the cold chain. And we wanted it to be able to do it with no grid power, all right? Because at these locations, you're not going to have grid power, and if you do have it, it's going to be very intermittent. And so that meant that we had to source our own power. Solar power was the most logical thing. We had to think of a cooling system, because we need active cooling now, and we need to be able to maintain this system for days at a time when there's no sun, or you might have to travel for 2 or 3 or 4 days to get there. But we realized that we needed to go longer than that. So we set our design goal to be able to go for 5 days with no power.
So a couple of things. We are going to put some temperature tracking and monitoring systems so that we can centrally monitor the system and make sure, identify that if any particular unit is not working properly, you should be able to replace it, maintain it, and service it. And also be able to do tracking of what children are getting immunized better than what the marker was doing on their finger.
Every year, around 2.2 million children die of diseases that could be completely prevented with adequate water and sanitation. It's about 6,000 a day. And things are failing too quickly to really make a difference. So this leads to the question of why. Why are things failing? Why is it that in 2012 we can put somebody on the moon many years ago, but we can't solve water and sanitation for a third of the planet? Now, this is a question that's really interesting to me, and it's a really important question to answer. It turns out that a lot of really talented and smart people have tried to solve this problem. And they've come up with a lot of really innovative solutions, but those solutions are failing too fast to make a difference. For example, these are all decentralized water treatment systems that I've come across in India. Every single one of them works really well in a lab, and every single one of them appears to be very appropriate for the environment in which it's in. Every single one of them was defunct in less than a year. The technologies themselves are not failing. The technologies themselves work in theory. What's failing is the system for maintenance, the system that's put in place to replace a part when it goes bad, to replace it when it goes missing, to keep it from disappearing in the first place, to do routine maintenance. These things don't exist. And that's what's happening to all of these filters. So we decided to think about things a little bit differently. We decided to look at the system of supporting the technology as being as important or even more important than the technology itself. You can't make this work unless you have a technology that operates so cheaply that you can sell it at a locally affordable price and still pay for the maintenance, and still fix it when it breaks, and still make a nice building, and still pay for quality control, and all of these other things, right? So that technology didn't exist in the mid-90s. And that's when Ashok Gadgil, who you saw speaking earlier about the Darfur Stove, started working on this in nights and weekends. And what he came up with was this. It's called UV Waterworks. What UV Waterworks does is it takes UV light and it cripples the DNA in living things so that they can't reproduce. It's very energy efficient. It's very cost effective. It's very effective in the sense that it meets international standards and kills all the pathogens. And it's very elegant because you don't have to add any chemicals to the water, and you don't have to add a filter that might clog. It's also very cheap. It costs about 5 cents a ton, or 0.005 cents per liter. That's about 25,000 times less than the last bottle of water you probably bought.
Last year, there were about 12 million cases of TB worldwide, and 80% of those were in Africa and in Southeast Asia and in countries like India and China. There were about 1 million deaths from TB worldwide, and again, 80 to 90% of those were in sub-Saharan Africa. The best way to prevent the spread of TB is to diagnose it early and then to start effective treatment. So we're still looking for an ideal test, one that's accurate, it's fast, it provides results to clinicians right away, it's simple to do so that it can be done in any lab or in any clinic in the developing world, it's inexpensive so that its reach is far, and then it can identify which drugs the patient's disease is sensitive to. So not that we just start any treatment, but that we start effective treatment for the patient. So the next step, once we have targets to go after, is then to develop a platform for detecting those targets. And for that, we're going to take advantage of a technology developed at the Berkeley Lab initially by Professor Gary Anderson. So what it is this little chip. It's a disposable plastic chip that I can keep in my pocket and hold in my hand. And what this chip contains is up to millions of features. And each feature contains millions of probes. And those probes, what they do is they go and find genetic targets, DNA targets. So this thing was initially designed to find for applications that require simultaneously detecting millions of different genetic targets. We're not interested in that many. There are probably about 100 or so genetic targets we need to identify in order to figure out whether someone has TB and whether they have TB that's resistant to one of several drugs that we use to treat TB. The other advantage of this chip is that once it's designed, it's very inexpensive to manufacture. Right? For every target, it just costs pennies to place onto this chip. So for about 100 targets, a chip with 100 targets can be manufactured for just a few dollars.